Susan for the invitation to be here. I'm honored to be invited to share my ideas with you, so I appreciate the opportunity. I'm going to build on what David just said, and I'm going to talk about something that I think we can do to move forward. That's the overall purpose of what I'm going to share with you. I was asked to talk about ATC's role in functional recovery, and to explain why you might care about that role, I was asked to explain a little bit about what ATC is and what ATC does, so I'm going to spend a few moments on that. Then I'm going to highlight just a couple of past projects of significance, because in today's context, they represent a couple of ideas for some things we might decide to do moving forward. Then I'm going to move as quickly as possible to what I think the most exciting stuff is that I'd like to share with you. It has to do with a brand new release, already mentioned a couple of times today, that I think serves the functional recovery objectives that we want to talk about today moving forward. And then give you my thoughts on some takeaways and what we can do. So, who is the Applied Technology Council and what do we do? In one slide, we were created by engineers for engineers, namely the Structural Engineers Association of California. We're a nonprofit organization. We use federal, state, and local government funding to do technology transfer to improve engineering practices. We're guided by a board of directors that have representatives from all the major engineering institutions from around the country and around the world. And we have a mission statement that talks about things like developing engineering stuff, being state-of-the-art, and being multi-hazard. But what I really like to say we do is we save the world one book at a time. Our project delivery model includes a small technical staff of engineers, of which I'm one, and really a very large group of technical consultants, of many hundreds of consultants that represent structural engineers and researchers, the best and brightest minds from around the country and around the world. Okay? And the key strategy for the development of our products is that disparate conglomeration of people. The end result is products that represent the best opinions from the smartest people and a broad spectrum of engineering opinion. That's the key strategy for what we do. If you think about what I like to call the technology development continuum, it begins with some kind of need. I don't know, let's talk about this functional recovery idea that we're here for today, okay? A bunch of smart people are doing some fundamental research wherever they exist around the country or world. Eventually that information matures enough so that engineers can use it in their practices, and eventually that information matures enough so that it becomes part of the standard of practice and the standard of care and finds its way into the building codes. Okay? Where ATC operates is bracketing that engineering box there, where we can accelerate the translation of fundamental research into engineering practice, or we can enhance and improve engineering practices to find their way into the standard of practice and into the codes. That's what we do and why we're here. We've been around a while, been around nearly 50 years, and typing that 45-year number actually gave me some pause. And we've produced more than 300 reports. I'm going to highlight 3. One called ATC 3, which was tentative provisions for seismic regulations for buildings in the 70s. One was ATC 14, which was a creative way of evaluating the seismic resistance of existing buildings in the 80s. And another was ATC 33, which developed a FEMA report, essentially guidelines for retrofit of existing buildings. And why are those important examples for today? Is because each and every one of those documents became a direct input to the codes and standards that we currently use for new and existing buildings in our current seismic design practices. They represent a model for how we can affect change in the future going forward. Okay, if you still don't know who ATC is, or you don't recognize those reports, we have something that I like to think of as ATC Scotch Tape. If you've been thinking about earthquakes, and you think about damage, and you think about post-earthquake safety investigation of buildings, even if you don't know who ATC is or ATC does, you probably have said ATC 20. Just like you might say, can you hand me the Scotch tape when you're wrapping your present? Even if your tape didn't come from Scotch brand companies, okay? So enough about the background. This is what I really wanted to talk about today, which is a new release. represents the end of a very long FEMA-funded project, as Mike mentioned earlier, the ATC 58 series of projects, and it produced a FEMA publication, which is actually a very large group, very large number of publications. There are 7 main volumes now, and over 100 background volumes documenting the information in this, which is intended to be the next generation for performance-based assessment of buildings and performance-based design of buildings, okay? And the exciting thing about that is it gives us a new technology that creates an opportunity for us to advance resilience concepts and advance functional recovery concepts going forward, okay? And if you think about the resilience context, we have regional and community scale contexts, and we have asset level, individual asset level contexts, okay? At the regional and community scales, we have things like FEMA's HAZUS, which is estimating losses around large regions, okay? And we have NIST Center of Excellence, which is developing a resilience estimation tool, calculating cascading effects and interdependencies. In contrast, FEMA P58 operates at the asset level. Okay, it's in that upper left-hand quadrant of what David was talking about in his last presentation. Okay, and the reason that's important to me, okay, is because at the asset level is where our current building design, construction, and procurement process exists. That's the paradigm, okay? And it's down at the code level where we can affect what we're doing. And my big point here is what we design today is the resilience that we will build tomorrow, okay? And this is where we can take action in the near term, okay, to reap the benefits in the long term. Sort of echoing something that Assembly Representative Nazarian suggested. Investing now for things that we can get later, okay? What does FEMA P58 provide? It provides probable consequences and explicit consideration of uncertainty for things like casualties, how much it might cost to repair damage, how long it might take to repair that damage, whether or not the building might be tagged unsafe, and if you care about it, what the environmental impacts associated with that damage might be. Why are those important? Because whether we've recognized it or not, we have been heading down the road, heading towards those kinds of things for a very long time. Like Chris said, we've been talking about it privately for 60 years, okay? In the 70s, the Blue Book outlined our foundational seismic design philosophy, which is resist small earthquakes with no damage, resist moderate earthquakes with some damage, and resist major earthquakes without collapse. Okay? In the 80s, the NEAR provisions started enhancing those definitions and expanding those definitions and making them more explicit, where we start talking about minimizing hazard to life, okay? Increasing the expected performance of higher occupancy structures, improving the functional capability of essential facilities, okay? And minimizing repair costs where practical to do so. And we were writing these things before we really knew how to do them, okay? We didn't know how to calculate repair costs in 2009, but we were writing these words, okay? In 2009, another ATC project produced another FEMA document which provided a quantitative definition now for that safety and a way of measuring it. And that created a cascading effect on our performance definitions, because in 2010, ASCE then adopted that criteria into structural reliability criteria that could be used. And it was placed in the ASCE commentary. And if that weren't enough, in 2016, now ASCE has migrated those reliability criteria into the standard itself. If you're doing performance-based design, you now need to meet reliability criteria. And that works on the structural side, and doesn't necessarily work yet on the non-structural side, okay? And the point here is that our performance needs have been evolving beyond life safety for decades. Some of the performance statements we've been using have been aspirational, and they've been inserted before we even knew how to do what we were doing, because we were saying what we wanted, and we were making change to the codes, and we saw in earthquakes maybe things were better, but we didn't really know how we were calculating it, okay? And the exciting thing right now is we have a tool that can actually quantify these things for us and help us inform the conversations we're trying to have at this critical time. How does it work? It begins, the methodology begins with calculations just like engineers are used to doing, and then it takes a left turn where it goes to attempting to explicitly estimate damage, and from that damage, estimate the consequences in terms of repair time, repair costs, etc. Okay? It does that through some numerical conveniences. My point here is to just show you that the methodology is based on estimating damage. Plant that seed. I'm going to come back to that point in a second. In doing our work to develop the methodology, we needed to test the methodology, and then we needed to exercise the methodology to develop the resulting design guidance. Okay? We had to do that for the purposes of our project, but that's very helpful for conversations like today because it now gives us a technical basis for looking at performance objectives and design guidance that could now be centered around functional recovery concepts. Okay. We did a bunch of work. The point of this talk is not to tell you about that work, okay? To tell you that it was based on a couple thousand designs, a lot of parametric variations, a couple 100,000 analyses, okay? Just fast forward to some results, some answers. Okay. What we found out when you measure current code conforming buildings using the FEMA P58 metrics, performance is not uniform across systems. So when you design different buildings and different systems using the same set of code provisions, you get different performance for those different systems. Okay? But importantly, on the plus side, you can control the performance with your design. Good thing, right? Otherwise, what are we doing here? Okay? And as I was mentioned by SK earlier, strength and stiffness are key, and strength and stiffness absolutely can control the performance that you're getting out of something like this methodology. And also, as mentioned earlier, risk category 4 criteria, which is what we use for our most important essential facilities, that criteria absolutely does improve performance over our standard occupancy structures. These are all good general results from what we know now, what our current seismic design provisions do as measured by this FEMA P58 technology. Let me drill down again, some numbers, okay? Huge story behind these numbers, okay? I want to show these numbers just to get a reaction out of you. My point here is just to tell you that they exist. Okay? There's too much story to explain to you today, but they exist. I have chosen as a slice out of this report healthcare occupancies because when we're thinking about functional recovery, an obvious starting point is hospital buildings. That's our risk category 4 healthcare occupancy. Those are the buildings that we expect to be able to go to right now, immediately occupiable following an event. And the top part of this table is there's also risk category 2 healthcare occupancies, and those are things that are not essential. Those are like our medical office buildings, and I'm showing these two to contrast some things. So let me just show two numbers. Okay? What if I told you that for a hospital building, repair costs might be 10% of the replacement costs? And what if I told you that it might take a month and a half to repair the damage to that hospital building? Okay? If you're not used to seeing these kinds of numbers, you might wonder if they're right or wrong. You might wonder what's a good number, what's a bad number. If you're used to looking at these kinds of numbers, you might have an opinion about whether those numbers are high or low. Okay? But if you're just an average person and you're just kind of thinking about things, you might say, gee, if I wanted to go to my hospital, what does it mean if they have damage that is taking a month and a half to repair? The point here is that data now exists and it's captured in a report, and we can use it now to have intelligent and informed conversations about what our seismic provisions might be telling us and what we might want to do to change those if we decide that these numbers are not good. Okay? So how can we use these going, I'll contrast that with the risk category 2 numbers just to show you the difference. Okay? For standard occupancy, that repair cost might be 20%, which is twice as big as it was for risk category 4, and the repair time might be 60 days, which is a third more. Okay? So the risk category 4 design criteria helps. Some things are working. So how can we use this information going forward? The FEMA P58 performance metrics now provide a way to have quantitative conversations about what is acceptable performance. Okay? What do those numbers mean, and do you like them? Okay? If those numbers are not good, then we can talk about how to set appropriate performance targets. What should the numbers be? Okay? And I told you this information was statistical. Okay? We can also talk about what kind of confidence do we need. Is it good enough that we have a 50-50 chance of making these targets, or do we need to be more certain? Do we need to be 90% confident that we're going to hit these targets? We need to look at the differences between systems and whether or not it's okay the systems are different, or whether we need to raise the different design criteria so that everyone's on an equal playing field. Not a trivial conversation, but we can talk about it. Okay? And we can use this information to define functional performance in quantitative ways that can be measured and adjusted with our seismic design provisions. And ultimately design buildings to achieve function. Some takeaways, what's been pounded into me since the day I started my career from people like Chris Poland: good seismic design is based on stable ductile performance. SK mentioned it today too. Okay? The problem with that in the resilience context is ductility is damage. And I told you this whole methodology is based on estimating damage. That is telling you that even our brand new code conforming buildings are expected to be damaged. Okay? I suggest that that's a disconnect between our current seismic design paradigm and the resilience concepts that we're talking now. Okay? Current seismic design paradigm is one earthquake buildings, may not be repairable. Resilience concepts are needing to use those buildings for more than just one event, for the next event. We're going to be in these buildings forever. Theoretically forever. So what can we do? Okay? Chris mentioned we've been having private conversations for 60 years. Okay? David mentioned different entities have been defining resilience for at least 10 years. Ryan suggested it's not an engineering question alone. Okay? But I would like to suggest that engineers can help. And we should take a leadership role in doing that. Okay? Performance-based design created with this beautiful idea. If we could just get people to tell us what they want, then we as engineers will provide them what they need. Okay? The problem with that is some of that information is really hard, it's very technical, and it's really hard for stakeholders to process and use. And some of it is intractable. What is an acceptable number of casualties? 0. Who can make a decision on what is an acceptable number of casualties? Okay? My suggestion is before performance-based design, engineers made decisions on behalf of society. Okay? We didn't do it in spite of society. We did it with society's best interests at heart. Okay? Codes were made safe because we knew people wanted safety. We didn't have to ask them, do you want a safe building or do you want to pay less on your building? Okay? We wanted safe buildings. Okay? From my perspective, it's now obvious that society wants resilience in some form, whatever we decide that might be. And my suggestion to us is that we need to create a code that offers a functional performance objective for buildings and infrastructure. It's not just buildings. Okay? And like Assembly Representative Nazarian said, it's a parallel effort across many areas, and we can use the building engineering model as a model that we can translate to other areas in the infrastructure area as well. Okay? It doesn't have to be mandatory. We can remove the roadblock of making it mandatory. Okay? If we can just avoid letting the perfect be the enemy of the good, and we can start some things where we know, and don't wait for other things to catch up. Okay? We can offer something to advance this conversation going forward. And I'd like us to really take those steps today if we would. So let's do something to build the resilience that we want tomorrow and start it today. Thank you.